All right, on number 1, we have to interpret the meaning of this statement, x equals log base 10 of 5200. So if we think about this as an exponential equation, this is really saying 10 to what power equals 5200. Remember, a log is always equal to an exponent. So if we think about some things that we know, well, I know that 10 to the third power is 1000, and I know that 10 to the fourth power is 10,000. So that means that the exponent on 10 that gets me 5200 has to be between 3 and 4. Okay, so this is our explanation, right? We can say something like 10 to the third power equals 1000, 10 to the fourth equals 10,000. Therefore, log base 10 of 5200 has to be between 3 and 4. On number 2, again, we are just interpreting what this is saying. So first, just how do we say this expression? Well, we would say this as log base 3 of 243. So what does this mean? Well, this means, if we think about this in exponential form, that 3 to some power equals 243. And then what is the value of this expression? Well, again, if we think 3 to what power equals 243, it ends up being 3 to the 5th power. So I can say that this expression then, log base 3 of 243, is equal to 5. Now, we can just type that into the calculator as well, right? We can type in log base 3 of 243, but this is the logic or the reasoning behind that. On number 3, a select all that apply question. So here we have a graph of 1 times e to the t, and we're told that it represents a population of bacteria t days after it was first counted. So let's go statement by statement and analyze here. So natural log of 30 is the number of days until the population reaches 30. Well, remember, ln, this notation, means natural log, or another way of saying that is log base e, right? So log base e of 30. So if I think about taking this equation and setting it equal to 30 and solving for t, well, I would divide by 1, and then I would have to take the log base e, or the natural log, of both sides, right? Or rewrite it using a log. So log base e of 30 equals t. So that is true, right? For B, the graph shows that 40 is a reasonable approximation for the natural log of 3.7. This statement is backwards, right? This should say that the graph shows that 3.7 is a reasonable approximation for the natural log of 40. So B is not true. C, natural log of y equals t is the logarithmic form of y equals e to the t. Well, again, if I think about just taking this exponential form and rewriting it as a log, well, I would say log base e, right, because that's the base of the exponential, of y equals t. And log base e is natural log. So C is also correct. On D, the value of e to the 2.5 power is greater than 10, so the value of natural log of 10 is also greater than 2.5. Now, I mean, we could just use our calculator and plug these in, right, to see what each of these values are. But we could also think about this on the graph, right? So let's try the calculator. Remember, e is right here, so if I hit second division, e to the 2.5 power is 12.1824. And then the natural log of 10 is 2.3, right? So this statement is not true. And the last one, the graph shows that 4.1 is a reasonable approximation for the natural log of 60. So if I go to 60, right, the corresponding t coordinate is just slightly greater than 4. So 4.1, I think, would be a good estimate. On the next few, we are solving each of these exponential equations. So the first step in solving an exponential equation is to get the exponential part by itself. So that means whatever is being raised to the power. So I need to get rid of this 4 out in front. So I have to divide both sides by 4. That gets me just 10 to the x equals, that would be 100,000. Now that I have the exponential by itself, now I can rewrite it as a log. So the base of the exponential becomes the base of the log. So this will be log base 10 of 100,000 equals x. I have the variable by itself. Now I can put this into the calculator. Now, this question says give an exact answer in logarithmic form. So here, this is our exact answer. But then if I put this into the calculator, that will get me the approximate. So remember, there's two options for this one. Since this is log base 10, I can just use the log button on the calculator. So I can do log base 10 of 100,000, and I get 5. So we'll say then that this is the approximate answer. So the exact answer I want in logarithmic form, and then the approximate answer is whatever you get when you type that in the calculator. On number 5, same thing. I need to get the exponential part by itself first. So I need to divide both sides by 5. So we'll get 10 to the 6x power equals 700. Now that I have the exponential by itself, I can rewrite this as a log. So log base 10 of 700 equals 6x. Remember, the log is always equal to the exponent. Now I still have one more step to get x by itself here. I still have to divide both sides by 6. So here, log base 10 of 700 all divided by 6, that is my exact answer. Then I can put this into the calculator to get my approximate answer. So again, base 10, so I can just use the log button. So log of 700. Now make sure that we close the parenthesis to show that I am dividing this whole thing by 6. That divide by 6 is not inside of the log, it's outside. So close the parenthesis, and we get, now we want to round to 4 decimal places. So if I'm rounding this to 4 decimal places, that would be 0.4742, right? Since the 5th digit is 5 or greater, the 4th digit would get rounded up 1 spot. So my approximate answer then is 0.4742. Same process on the next one. To get the exponential by itself first, so I need to divide both sides by 3. So I end up with 2 to the x equals, now 3/8 divided by 3 would just be 1/8. Now, if you're going to put that in your calculator, right, if you just do 3/8 divided by 3 like that, that will work in this case. We get this decimal, and remember that we can change that back to a fraction if we want by hitting the math button and then the first option, but we don't have to. We can just leave it as 0.125. Now I have the exponential by itself. I want to rewrite this as a log. So this would be log base 2 of 1/8 equals my exponent. So in this case, my exponent is by itself, or my variable is by itself, so this is my exact answer, and I can put this into the calculator then to get my approximate answer. Now remember, if I want a base other than 2, I have to go into the math menu and then scroll until I get to log base. So now I can put in log base 2 of 1/8, and I get -3. So we'll say that that is our approximate answer. Same idea on number 7. Get the exponential by itself first. So I'm going to divide both sides by 3. So I will have e to the x plus 4 power equals 17. So I have the exponential part by itself. Now I can rewrite this as a log. So this would be log base e of 17 equals x plus 4. And remember, log base e is the same thing as natural log. So this is going to be natural log of 17 equals x plus 4. I still have one more step to get x by itself. I have to subtract this 4 over to the other side. So I end up with natural log of 17 minus 4 equals x. Be careful here. This is not the same thing as natural log of 13. That 17 is trapped inside of the natural log, so I cannot just subtract 4 from 17. I'm subtracting 4 from the natural log of 17, so I would have to type it into the calculator like this. Now again, remember, this is the exact answer, and then when I type that into the calculator, natural log of 17, close the parenthesis, and then minus 4, we get negative 1.1668 if I round to 4 decimal places. And that is what we would put in for the approximate answer. On number 8, we have a function that models the population of a town in millions, and our time is measured in years since 2000. So what is the annual growth rate as a percentage? Well, to get that, I'm looking right here, okay? This 0.025. That is my percentage, or I'm sorry, that is my growth rate as a decimal. So to convert that to a percentage, I just need to move the decimal over 2 spots, and I get a 2.5% growth rate. What is the population in the year 2015? Well, I just need to take this function, and since this models years since 2000, I'm going to plug in 15 for t. So I'm evaluating p of 15, so 3.1 times e, 3.1 times e to the 0.025 times 15 power. So if we put that into the calculator, 3.1, remember e is right here, so second divide, 3.1 times e to the 0.025 times 15 power. And again, let's round to 4 decimal places. So this would be 4.5105. And remember, this is in terms of million. So 4.5105 million. Now, how many years will it take for the population to triple? Well, just by looking at my function, I see that my initial population is 3.1 million. So triple that would be 9.3, right? Triple just is multiplied by 3. So I want to take my function and set that equal to 9.3 and solve this equation for t. So the first thing I'm going to do is divide both sides by 3.1. So I end up with 3 equals e to the 0.025t. So now I have the exponential by itself. Now I can rewrite this as a log. So this would be log base e, or the natural log of 3 equals 0.025t. I still have one more step to get t by itself. I need to divide both sides by 0.025. And now I can put this into my calculator. So natural log of 3, close the parenthesis, divided by 0.025 gets me 43, and again, if we round to 4 decimal places, 43.9445. Okay, so almost 44 years for the population to triple. On number 9, we have 2 graphs, right? So, and they represent the number of views of 2 different websites, t days after they were posted. So what does the point of intersection tell us in terms of the context of this situation? Well, that would be at what point in time the 2 websites had the same number of views. What are the approximate coordinates of the point of intersection? So here, I mean, we don't have any way of solving this. We are just using the graph to approximate. So, I mean, I don't know. It looks like maybe 870, I think, would be a good approximation. So what that means is 8 days later, they had about the same number of views, and that number of views was 70. Now, part C, we are given the function for the views on website A, and we want to figure out when the number of views will reach 1,000. So all I'm doing is setting this function equal to 1,000 and solving. So 32 times e to the 0.065 t power equals 1,000. So to solve, start by dividing both sides by 32. So e to the 0.065 t equals, now I'm not even going to bother putting this in the calculator yet. I'm just going to leave this as 1,000 over 32. I don't want to try to round an intermediate step here. Now I have the exponential by itself, so I can rewrite as a log. So log base e, or natural log of 1,000 over 32 equals my exponent, 0.065 t, and then one last step to get t by itself, divide both sides by 0.065. So this is what I want to put into the calculator. So natural log of 1,000 divided by 32, close the parenthesis, divided by 0.065, and that gets me, again, round to 4 decimal places, 52.9541. All right, so after almost 53 days, they get to 1,000 views. On number 10, we have 2 different functions modeling influencer A's and influencer B's subscribers. We want to figure out at what point or after how many months they have the same number of subscribers. So I just want to set these 2 functions equal to each other. So 10 times e to the 0.075 m equals 15 times e to the 0.06 m. So to solve something like this, I want to start by dividing or getting my coefficients on the same side. So I'm going to divide both sides by 10. So I get e to the 0.075 m equals, so here I'm just dividing the 15 by 10, so that would be 1.5 e to the 0.06 m. Now I want to get my exponentials on the same side. So I'm going to divide both sides by e to the 0.06 m power. Now when I do this, on the right side, obviously these cancel out. But on the left side, when I am dividing two things with the same base, I subtract the exponents. So 0.075 m minus 0.06 m, I mean, we could put those values into the calculator, but if I'm subtracting those, that should be 0.015 m equals 1.5. Once I have it down to here, now this should hopefully look pretty similar. We have the exponential by itself. I can just rewrite this as a log. So log base e, or natural log, of 1.5 equals my exponent, equals 0.015 m. And then last step to get m by itself, divide both sides by 0.015, and we can put that into our calculator. So natural log of 1.5, close the parenthesis, divided by 0.015 should get me 27, and again, round to 4 decimal places, so 27.0310. On number 11, we are given the graph of some logarithmic function, and we have to figure out what the base of the log is. Well, if I look at some exact points, I see the point 5,1 and the point 25,2. Those are exact coordinate points that I see. So we are trying to think, okay, we've got log base something of my x value equals my y value. So interpreting this, we're trying to figure out, okay, what to the first power equals 5? Well, 5 to the first power equals 5, right? That means that the base of the log has to be 5. So we're given a few other coordinate points then. We have to fill in the missing coordinate. So here, if I know my log base is 5, right, here we're thinking, okay, well, log base 5 of what equals 0, right? The x value is what would be inside of the log, and the y value is what my result would be. So here, well, 5 to the 0 power equals 1, right? So this coordinate point would have to be 1. This one, we're thinking backwards now, right? So now I'm thinking I have the x value, so this would be log base 5 of 625 equals what, right? So we could just put this in the calculator or think 5 to what power equals 625. Well, it ends up being 5 to the 4th power. And then the last one, kind of like the first one, right? We're saying log base 5 of what equals -3. So if I think about this in exponential form, 5 to the -3rd power equals what I need to put here, right? So that would be the same if we're thinking about our negative exponents as 1 over 5 to the 3rd, and 5 to the 3rd is 125. So this would be 1 over 125. On the last one, the area of a wall covered by mold will double every month if left untouched. So we need to complete the table with that in mind. So let's think about a function to model this situation, right? I know that if I'm doubling every month and we started with 1 square foot, well, our starting value of 1 times our growth factor of 2 to the x power, right? Or let's use the m power for months equals the area. All right, well, dividing by 1, I could simplify this function and just make this 2 to the m power equals a. So here we have to kind of think backwards. We have to think, okay, what exponent is going to get me this result? To do that, the easiest thing that we can do is rewrite this equation as a log. So I could say this would be the same thing as log base 2 of a equals m, right? So here I'm thinking log base 2 of my area of 2. So 2 to what power equals 2? Well, that would be 1. Here I'm thinking log base 2 of 16. So 2 to what power equals 16? That's 4. For the next one, log base 2 of 20. Well, 2 to what power equals 20? This one is not a nice exact value. So this one we can use the calculator for. So if I go to my calculator, math, log base 2 of 20, we get approximately 4.3219. For 32, again, same thing, right? 2 to what power is 32? This one is, again, a nice value. That's just 5. 2 to the 5th power is 32. This one, log base 2 of 64. So 2 to what power is 64? That's just 6. And then the last one, 2 to what power is 100? This one, not a great value again, so we'll have to use the calculator. So math, log base 2 of 100, and I can say that that is approximately 6.6439 if we round to 4 decimal places. Now, the last one is basically just asking me to extend all the way down to 240 square feet. So using this same logic, I can say that this would be log base 2 of 240. Right? And again, tells me to round to 4 decimal places. So we can put that into the calculator. So math, log base 2 of 240. So this would occur after approximately 7.9069 months.